Welcome to this comprehensive training video on thread-safe collections in C#. This is an absolutely essential topic for any beginner looking to build robust, reliable, and high-performing multi-threaded applications. Understanding these concepts is fundamental to modern software development. Thread-safe collections are crucial tools in C# for effectively managing data in multi-threaded applications. They are specifically designed to ensure that multiple threads can access and modify collections concurrently without causing critical issues like data corruption or unpredictable race conditions. This capability is vital for application stability. These collections provide robust, built-in synchronization mechanisms, which significantly simplify multi-threaded programming and make it much safer. This is especially true in complex scenarios where numerous threads need to access and modify shared data simultaneously, such as in server-side web development or responsive UI applications. Thread safety is paramount when multiple threads access shared resources concurrently. Without proper synchronization, race conditions can easily occur, leading to unpredictable behavior, incorrect results, and severe data corruption. These issues can be extremely difficult to debug and resolve if not prevented from the outset. It's important to understand that standard collections in C#, such as list, T, and dictionary, T-key, T-value, are not inherently thread-safe. This means that concurrent access to these collections from multiple threads can lead to significant and often subtle issues, making them unsuitable for direct use in multi-threaded environments without external synchronization. The system, collections, concurrent namespace in C# provides several key thread-safe collection classes. These classes are specifically designed and optimized to handle concurrent operations efficiently and safely, offering robust solutions for common multithreading patterns. Concurrent dictionary, T-key, T-value, is a highly efficient thread-safe dictionary. It allows concurrent read and write access, making it ideal for scenarios where keys and values are frequently added, updated, or removed simultaneously by multiple threads without contention. Key methods within concurrent dictionary, such as try-add, try-remove, and get or add, are atomic. This means they are guaranteed to complete their operations without interference from other threads, thereby maintaining absolute data integrity and consistency even under heavy load. Concurrent QT is a thread-safe FIFO, or first in, first out, queue. It is designed so that multiple threads can safely enqueue new items and dequeue existing items simultaneously, ensuring that items are processed in the exact order they were added. Concurrent stack, T, is a thread-safe LIFO, or last in, first out, stack. This collection allows multiple threads to safely push new items onto the top of the stack and pop items from the top concurrently, following the last in, first out principle. Concurrent bag, T, is a thread-safe, unordered collection. It is specifically designed for scenarios where multiple threads frequently add and remove items without requiring a specific order, making it highly efficient for producer-consumer patterns where order is not critical. Blocking collection, T, is a versatile thread-safe collection that supports adding and removing items with powerful blocking and bounding capabilities. It is perfectly suited for classic producer-consumer scenarios, allowing producers to block if the collection is full and consumers to block if it's empty. The benefits of using thread-safe collections are numerous and significant, starting with their inherent thread safety. This built-in safety completely eliminates the need for developers to implement complex and error-prone manual synchronization mechanisms, saving considerable development time and effort. This inherent safety significantly reduces the risk of race conditions, which are common sources of bugs in multi-threaded applications. By preventing these issues, thread-safe collections make your multi-threaded code far more reliable, predictable, and easier to maintain. Furthermore, thread-safe collections often offer superior performance in multi-threaded scenarios compared to manually implementing synchronization using traditional locks or monitors. They are optimized for concurrent access patterns, leading to more efficient execution. Concurrent collections achieve this performance advantage by utilizing advanced techniques such as fine-grained locking and sophisticated lock-free mechanisms. These methods minimize contention between threads, thereby optimizing execution speed and overall application responsiveness. Finally, These collections dramatically simplify code by removing the need to implement complex manual synchronization logic. This allows developers to focus their efforts on core application features and business logic, leading to cleaner, more readable, and more maintainable code bases. Now, let's dive into some practical demonstrations to see these concepts in action. We'll begin by setting up a Visual Studio Console application to illustrate the fundamental principles of thread-safe collections in a controlled environment. Our first scenario involves simulating multiple threads concurrently adding data to a shared collection. This demonstration will clearly showcase how thread-safe collections effectively handle this concurrency, preventing data corruption and ensuring consistent results. For this demonstration, we'll specifically use concurrent dictionary T-key, T-value, to store data that will be accessed and modified by multiple threads. This will effectively demonstrate its robust effectiveness in managing shared state in a multi-threaded context. We will create multiple threads, and each thread will concurrently attempt to add or update data within the dictionary. This setup will highlight the seamless and thread-safe operations provided by concurrent dictionary, even under simultaneous access. Observe closely how methods like triad or add or update ensure complete thread safety. These atomic operations prevent any conflicts and maintain absolute data integrity, even when multiple threads are trying to modify the same entries at the same time. A helpful tip for beginners: you can create and start new threads using the thread class, which is part of the system threading namespace. This provides fine-grained control over thread execution and is fundamental for understanding lower-level multithreading. Another useful tip is to demonstrate how to use parallel from the task parallel library. This construct makes it incredibly easy to create parallel loops, significantly simplifying many multi-threaded tasks and improving performance for CPU-bound operations. You can also monitor the state of the collection using the Visual Studio Debugger. Setting breakpoints and inspecting the collection's contents during runtime is an invaluable technique for understanding and troubleshooting complex concurrent operations. Next, we'll transition to exploring thread-safe collections within a Unity 3D project. Our focus here will be on the critical task of safely updating UI elements from background threads, a common and challenging requirement in game development. Our Unity scenario involves updating UI elements from multiple background threads that are loading assets. This is a very common challenge in game development, where asset loading can be time-consuming and needs to happen without freezing the main thread. To facilitate safe communication, we'll use concurrent queue T to pass data from these background threads to the main thread. This ensures that UI updates happen safely and correctly, preventing common Unity threading errors. A background thread will be responsible for loading assets, such as textures or models, and then enqueuing them into the concurrent queue T. This effectively simulates an asynchronous loading process, keeping the main thread responsive. In the main thread, we'll continuously dequeue the loaded assets from the concurrent queue and use them to update UI elements. This demonstrates the crucial safe interaction pattern between background worker threads and Unity's main thread. It's critically important to emphasize using a Unity main thread dispatcher or a similar pattern to execute code on the main thread when interacting with Unity's API. Directly accessing Unity objects from background threads will lead to errors and crashes. Another helpful tip is to explain how to use async and await for asynchronous operations in Unity. These keywords simplify complex multithreading patterns, making code more readable and manageable while still achieving non-blocking operations. Also, we'll demonstrate how to use the lock keyword to protect shared resources when necessary, even when working with thread-safe collections. While thread-safe collections handle their internal state, external shared resources might still require explicit locking. While incredibly powerful, thread-safe collections generally incur some performance overhead compared to their non-thread-safe counterparts. This is primarily due to the necessary synchronization mechanisms they employ to ensure data integrity. For applications with very write-heavy workloads, consider alternative strategies such as partitioning the workload. This involves dividing the data or tasks among multiple collections or segments, which can maximize performance and significantly reduce contention. Querying aggregate state, such as calling .count or .isEmpty on a thread-safe collection, can sometimes require locking the entire collection internally. This can potentially block multiple threads, impacting performance, so be mindful of how frequently these operations are performed. When working specifically with Unity 3D, it's absolutely crucial to interact with Unity's API only from the main thread. Attempting to modify game objects, components, or other Unity-specific objects from background threads will inevitably lead to errors and crashes. To achieve efficient thread safety in Unity, you can leverage Unity's built-in native container objects or use blittable types. These are optimized for performance and safe use with Unity's job system, providing a powerful alternative to standard C# collections. The job system in Unity is a powerful framework that allows you to write multi-threaded code easily and safely. By creating jobs instead of raw threads, Unity manages the threading details, ensuring optimal performance and preventing common threading pitfalls. It's important to understand Unity's custom thread-safe types like native list, T, native queue, T, and native parallel hashmap, T-key, T-value. These collections are specifically designed for use with the job system and offer optimal performance within the Unity environment. A key strategy for performance in Unity's job system is to mark collections as read-only when appropriate. This allows for concurrent read access from multiple jobs simultaneously, significantly enhancing parallel processing capabilities without risking data corruption. Consider implementing thread-safe operations using tasks from the task parallel library instead of traditional raw threads. Tasks offer a more flexible and manageable approach to asynchronous programming, simplifying error handling and cancellation. By diligently following these guidelines and appropriately utilizing thread-safe collections, beginners can confidently write robust, efficient, and highly performant multi-threaded applications in both Visual Studio Console applications and complex Unity 3D projects. Thank you for watching this comprehensive training video on thread-safe collections in C#. We sincerely hope you now have a solid and practical foundation in understanding and applying these essential concepts for your future multi-threaded development endeavors.